There's the shore code. And then week 2, we had Anand, and he showed us the toric code. Okay. And plus, we also saw the stabilizer formalism for a code. So I'm just going to assume that everyone is at least familiar with that to some degree. And today, what I'd like to show you guys is the CSS formalism, which is a subset of stabilizers. And the CSS, those letters stand for Calderbank, Shore, Steen, and named after the authors who first developed this formalism for codes. So the high-level way of thinking about these guys is they are just stabilizer codes where the generators are all X or all Z. So that means that each generator is just written as, x1 times x2 times x3, something like this, et cetera, et cetera. And both of the codes we saw previously concretely, the Shore and the toric code, are both forms of CSS codes. So what applies right now is true for those codes in general. So just a notation that's going to be very useful is we're going to refer to x to the a. Okay, this is an operator. And what this means is it's x, it's the tensor product of x, where the index of this guy is going to be, here, let me do this way, is going to be x to the a1, tensor x to the a2, tensor dot dot dot, tensor x to the an, for a being a vector in 0, 1 to the n. So it's just a way of, it's a short form of writing, this big tensor product, where some of these guys are going to be identity. So like if a2, for example, is 0, then this component would be in the middle. So it's just going to be a very short form that we're going to use. And analogous, we would look at z to the a if we need to. Okay. So recall the property that we really involved in our stabilizer codes was that checks commute, right? So stabilizers have commutation. And so in this case, if x to the a and z to the b are stabilizers for my code, right? The commutation result is very simple to write. It's just that the inner product of the two vectors a and b has to equal 0. Okay, so this is just a general property of these stabilizers and the fact that we're using these Pauli operators, and this is because the Pauli operators x and z anti-commute. So we need the number of places at which these two elements x to the a and z to the b intersect has to be an even number. So that's equivalent to the inner product equaling 0. The inner product here is over f2. Okay, is that part clear? Okay. So I'm moving on to the second page. So if my stabilizers are x to the a1, all the way to x to the a, let's call it jx, and z to the b1, all the way to z to the bjz, say, are my stabilizers, right? Then there's a succinct representation for the condition that everything works out, which is that I would need the following matrix product to equal 0. So if I write, the vectors of A horizontally, something like this, and I look at this matrix, and I look at another matrix, which is just all the vectors B, B1 through BJZ, this way, I require that this product is indeed 0, right? This was just going to be this is a necessary condition if we are to talk about these stable S's in the first place. Is that so far so good? So, right, so if you just, right, because you need the inner product between any vector AI and any vector Bj to be 0, so that's exactly what the entire matrix checks out. Okay, so let's first look at this in a slightly different picture, and this picture is going to be motivated by topology, but I think it's very helpful, especially as we move forward in this line of work towards these fiber bundle codes, to look at it this way. Is let's look at an idea from topology called a chain complex. So chain complex is nothing too fancy. We start with vector spaces, so we're going to start very simple with just vector space F2 to the A2. A2 is just a set here, and a map we're going to call it delta 2 onto a vector space F2 to the A1. Okay, and then a map from here, a boundary map delta 1, and is at F2 to the A0. And we're going to have a condition that we're going to involve, which is that delta 1 times delta 2 is equal to 0. So this is going to be our condition. Such that. Okay. And this picture, in the following picture, well, we actually, another way to see this is if we thought about this matrix here as my matrix delta 2, and I thought of this matrix as delta 1, this is in effect a generalization of what I wrote, just if I kind of wrote this in this weird kind of vector space world. Is everyone okay so far? Okay. So this chain complex, right now, I mean, I've just stated as this vector space with these maps, but there's a very quick mapping from this chain complex back to the code results, which is we can think of A2 as the set of Z.
So there's a question in the chat.
Oh, okay. Could you read it out?
Sorry, is Jx a product J times X?
Oh, no, that's a J subscript X. Just yeah, that's here. I could make this simpler. This is J and J prime, say. Yeah, just to note that there are two different, that they could be two different sizes. So the number of X checks and the number of Z checks don't necessarily have to be the same. That's all I wanted to note by that. So the number of X checks is called J, and the number of Z checks is called J prime. Yeah, great question. So we're going to look at A1. Sorry, A2 is the set of Z check generators. A1 as the set of physical qubits. And A0 as the set of X check generators.
When you say the set of Z check or X check generators, do you mean like an independent set of generators?
Right now, we don't actually need the generators to be dependent. So I can always, even if my set has dependencies in it, I can still think of those as the same set. So if I took this matrix here, and I added another row, which was a linear combination of the previous rows, right? It would still satisfy this property that that this matrix multiplication would still equal 0, right?
Right, but would it change? Would it change what A2, A1, and A0
are? Yeah, but we can still, the boundary map would still be well defined. So
okay.
I'm just thinking of this as a set of generators for my Z checks, and even if there are redundancies, that's okay. Yeah.
Okay.
So checks are the same thing. No, go ahead, William.
I never mind.
And so here are checks the same thing as stabilizers?
Yeah. Well, okay, so let's be precise here. We're going to think of stabilizers as all the possible multiplicative combinations that we can get when we multiply these different checks together. So the crucial property we're going to have is that we're going to identify some checks which are some stabilizer terms which are exclusively all x or all z. Now, my stabilizer terms, even if I start off with some that are all x and all z, I can multiply them together and get another element of the stabilizer group that won't be, all x and all z. Once I multiply two of them together, I'll get something which is a combination of x's and z's, right? But I'm really interested in finding out stabilizer groups which have a basis or a set of generators which are all x's and all z's.
Okay, I see. Thank you.
Yeah. So, right. So the stabilizer group itself might become a little tedious to work with, but the nice thing about this is that everything here is going to be very linear. And so in order to understand the space of things that we're working with, it's very helpful that if we can just talk about the generators. So the generators are all going to be just x checks or z checks. Yeah. So this point, it might be illustrative to actually look into an example. Okay. So recall on the Torah code. Inside the Torah code, so let's look at a region of the Torah code, which looks maybe something like this. This is somewhere, within the torus. We zoom in on a section of the torus, we'll see something like this. And let's denote some regions. So we're going to have a face, so let's call it alpha. Let's call the vertices that are touches, let's just give them numbers 1, 2, 3, and 4. Okay. Let's call these sides A, B, C, and D. Okay. So recall in the Torah code construction that Anand talked about last week, right? Given a face on the torus, we had a check which was all the edges that touched that face, right? So in this case, in our example, we could see the delta 2 operator for in this chain complex as just the vector 1, 1, 1, 1. It takes that one face to an indicator on each of the 4 vectors, right? Together. And the other vector is going to be this matrix here. And this will be my delta 1 vector. It takes my set of edges to the vertices adjacent to it. Right. So that's one way to look at this boundary map, and one can easily verify that delta 1 times delta 2 here is actually indeed 0. Anand, you look a little confused.
I have a question. So I should think of delta 1 as like, let's see, if delta 2 is like the z checks, I'm mixing them up.
Yeah.
Then delta 1 should kind of contain the x checks. So
delta
it should
1,
really.
Right. So you got to be a little careful here. The delta 1 won't contain the x checks. Its transpose defines the x checks. So if you go back one page, you'll see that in the 2 matrices have to be in order to get the inner product, right? One of them has to have the checks described vertically, and the other one has to have described horizontally.
Sure.
So
yeah, I guess my question was like, when I think of the x checks, I mean, they're a vertex check, right? So there are 4 edges, and so you should have like 4 ones in a column or 4 ones in a row, whichever the orientation is. And so is this just like we're just looking at this one plaquette and we're forgetting about all the other ones for a second?
Right. Yeah. Let's actually, yeah. So we can still define the code even if we remove all this extra fluff here, right? Even if we just had this object which just looked like this, that would be okay, right? So yeah, sorry, I should have more simply. So even if my graph from which I'm defining the code looks like this, it's just the good old fashioned square. Yeah, this is exactly what I would get out.
So just to clarify, what would be A1 and A2 in this example?
Great. So yeah, so in this set, A2 is going to be the set alpha. A1 is the letters A, B, C, D. And A0 is this numbers 1, 2, 3, 4. So, right, so I can think of delta 2, right, as now it's kind of easy, maybe it's a little easier to see now why it's a map from the space over the vector space over A2 to the vector space over A1, right? Because it takes a 1D space into a 4D space. That's what the vector delta 2 does, and then the vector delta 1 takes you from a 4D space back to a 4D space.
I see. So when you write f2 to the power a2, it just means a vector space of the cardinality of the set you put in the top.
Right. In particular, it's nice because we can identify a basis with each of those, within everything in A2 and then everything in A0, etc.
Thanks.
Yeah.
I'm a little confused when you say that delta 2 and delta 1, when you multiply them, it equals 0. Doesn't it?
So, okay, good. So let's think of, so we're thinking of delta 2 as a map from the vector space over A2 to the vector space over A1. Right? So maybe I should be a little bit more pedantic here. This matrix here, the size of this is going to be size A2 by size A1. So a map from the vector space of dimension A2 to vector space of dimension A1 is precisely described by a matrix that is of this shape here, right? That's because we're just going to linear maps. So this map is well defined by such a matrix, right? And this matrix is just going to be popular with ones and zeros. It's a matrix over F2. And
should that have been delta 2 then, since it's going from A2 to A1?
Oh, I'm so sorry. This should be A1 to A0. Sorry. And then this guy is again A1, and this one is A0. Yeah, sorry. Yeah, A2. Yeah, delta 2 takes you from A2 to A1, and then delta 1 takes you from A1 to A0. Okay, yeah, thanks.
So then in the next page, they don't multiply to 0 though. Don't they multiply to 2, 2, 2, 2? Or am I misinterpreting multiplication?
Right. So no, you're doing absolutely right. But all our math is over F2. So
Oh,
yeah,
I got it. Thank you.
Yeah. So the field here is F2. So yeah, exactly. So they do multiply to 0 indeed. Yeah. Yeah. Are there any other questions here? So right at the moment, all we have done is we've just said, let's think about a stabilizer code where all the generators look like all X's or all Z's. We notice that if we have such a requirement, we actually get this condition that we described as a matrix product. And then we said, let's do this one step further, which is let's write out this chain complex. So the chain complex is nothing too fancy. It's just saying I'm identifying what the dimensions of these matrices are, these delta 1 and delta 2 matrices, and I'm writing out that product in this chain complex way. And that's all we've done so far. We haven't said anything about like the distance or the rate or anything of this nature, and we'll soon get to that properties as a function of these maps. So I'll just write this out one more time on this page so that we don't have to keep going back and forth. Okay, so looking at how we kind of came to this object, we can see the span of the Z stabilizers. So let's consider the Z stabilizers as everything that's generated by the Z checks that we identified in the beginning. This guy is going to be the image of the map delta 2, right? Because delta 2 was that we created the map delta 2 by saying every generator, here's the faces it maps to. So if I look at a combination of those, right, I said, let me multiply any two of those. That's the same thing as adding up those indicator vectors. So I can get that the span of the Z stabilizers will just be the image of the delta 2 map. And so it's kind of nice. We've taken this product thing and we're just moving it to just this linear algebraic statement about delta 2. That's so far so good. Okay. So now here's the one that might be a little trickier to see is the span of the X stabilizers is going to be the image of delta 1 transpose. Sometimes written with a star in algebraic topology, but it's the same thing. It's just the matrix transpose. And one thing to note that this guy is actually equal to the kernel of delta 1 transpose. But this is, when I do perpendicular here, this means everything perpendicular to that. Sorry. Is this fact here? This is a linear algebra fact, but I can show it why it's true if anyone's curious or doesn't see it.
Sorry, just to clarify, is delta 1 star, what is it?
It's the transpose.
Okay.
So delta 1 is a map from A1 to A0. So delta 1 transpose is a map from A0 to A1. It's just if you took the delta 1 map and you took the transpose of that matrix, it would give you a map going the other way, right? So, yeah, so delta 1 transpose just sits right here. And analogously, there's going to be a delta 2 transpose here. Okay, so we at least see the span of all my X stabilizers as just this image of delta 2, right? Is that part clear? And then the span of Z stabilizers the image of delta 2, and span of X stabilizers as the image of delta 1 perp, just because of the way we wrote out this stuff. Okay.
Wait, can I get like 10 more seconds to stare at this last equality?
Yeah.
Cool.
Yeah, this one. Yeah.
Oh yeah, thanks. Yeah, I would appreciate a proof. That'd be great.
Yeah. So, okay, if X is in kernel of delta 1 and Y is in the image of delta 1 perp, we want to show they're orthogonal, right? So how do we show they're orthogonal? We want to compute X, Y. Okay. But if Y is in the image of delta 1 perp, right, then Y is equal to delta 1 perp of something else. Let's call it Y tilde, right? Okay, but this is a linear map, so I can move my delta 1 across the inner product, right? And I get this. But now X is in the kernel of delta 1 perp, so this guy is 0 on the left side. So I'd change the inner product of 0 and Y, which is 0. So this certainly shows that everything in the kernel is perpendicular to the image of this. Now, to show that this is complete, you have to make a dimensionality argument, but I won't do that part. But maybe at least this is this is half of the argument you have to make.
Thanks. Yeah, I'll stare at this, but you can keep going.
Okay. Yeah, right.
Sorry,
So-
can I ask why the span of the Z stabilizers is the image of delta 2? I thought A2 were the Z stabilizers and A1 were the X stabilizers. So the image is A1? Okay.
So image of delta 2 is going to be a subset of A1, right? It's going to be, image of delta 2 is contained in F2 to the A1, but it may not be So let's imagine the following thing, right? I have an X. I start off with all my generator terms for my Z checks, right? And I take two of them and I multiply them together. That's going to be now going to be a Z stabilizer that's on the sum of those of their indicator vectors, right? So maybe I should write it this way. If I have ZA and I have ZA1 and I have ZA2, this product is the same thing as Z on A1 plus A2, right? Where the addition with respect to F2. So if I start off with my Z checks being, ZA1 to ZAJ, right? What are all the different Z checks that are in the stabilizer group? Well, any ZB such that B is in the span of A1 through AJ is certainly going to be is a stabilizer, right? This is all of them. Because it's
Thank
stabilized.
you. Yeah, that's good. Great.
Right? And so the span of A1 through AJ is, if I think of them as a matrix, this will be precisely the image of delta 2. Yeah, it's not easy to see, right? But what we've really done is we've said, let's take our world of these products of Pauli checks on different things, and instead of thinking about the Pauli checks themselves, we really want to deal with their indicator vectors. Right. So so let me be more precise then, maybe that wasn't clear, is that when I think of the span of Z stabilizers being the image of delta 2, I mean that any vector in the image of delta 2, if I treat that as an indicator vector for a Z check, that Z check will be a stabilizer. Is that help a little?
Yeah, that's good. Thanks.
Okay, great. So this is kind of nice. At the moment, we've just identified all the stabilizers, which look fully Z or fully X. But what we really want to understand is, what are the stuff that is not just a stabilizer? Like, how do I reason about the rest of the space, right? So let me go on to page 4. Okay. So recall for a stabilizer code generated by group G, by set G. Okay, so now this is in the Pauli's. The stabilizers are just whatever can be generated by G. So if I take all the products, so now not just the X's, not just the G's, but all the products together. And the logical operators are anything which are in the commutator of that group, set minus what can be generated by that group. Right? So this is something Anand talked about last time. And so what we should do is our goal should now be to calculate the logical operators for our CSS code, which our CSS code recall is going to be just defined by delta 1 and delta 2, right? Okay. So first thing, this is a fundamental kind of result that we're going to need, is note that delta 1, delta 2 equaling 0 implies that the image of delta 2 is well contained in the kernel of delta 1. They may be equal, but it's certainly a subset. Maybe it's just a subset equal to. Is that okay with everyone? Okay, I'll take that as a yes. Okay, so let's do a fun claim. Just claim. Okay. Any vector v in the kernel of delta 1, okay, implies that z to the v commutes with all x and z stabilizers. Okay, so I'm gonna find something which is certainly going to be in the commutant, but I'm not claiming that it's necessarily outside of G. Okay, so we need to do two parts, right? One part is easy. It certainly should commute with all the Z stabilizers. That's trivial, right? It just has to because it's a Z type. But now, how do I show that it commutes with all the X stabilizers, right? Well, any X stabilizer, right, by the previous thing we said is in the image of delta 1 perp, which is precisely equal to kernel of delta 1 perpendicular. So therefore, that, and this guy is in kernel of delta 1, this is in kernel of delta 1 perp. So clearly, they're orthogonal. Okay, sorry, I used some short form here that may have been a little annoying. Is when I say any X stabilizer, I mean the indicator vector for that X stabilizer, right? The indicator vector for that X stabilizer is going to be the image of delta 1 perp. So yeah, maybe I should be clear. So if I have an X stabilizer, X to W, and W is in this, therefore VW is equal to 0, and X to the V commutes with Z, sorry, W, is that okay? Okay, right. And the corollary that one could look at in the other direction, right, is any W in kernel of delta 2 perp, then X to the W commutes with all X and Z stabilizers. Is everyone okay with this so far?
Is it the same reasoning that you used in the previous slide?
Right. Yeah, exactly. No. So yeah. So is that Anurag speaking?
Yep.
Yeah. So exactly, it's exactly the same, right? Right now I'm thinking of my cell complex as going this way, as going from A2 to A1 to A0, right? With maps of delta 2, delta 1, right? But just flip your head sideways, and I can think of it as a cell complex going from A1, from A0 to A1 to A2 with maps delta 1 perp and delta 2 perp, right? So if I just flip the picture around, I get the same object, right?
Yeah.
Yeah, so exactly. So what you prove in one direction, you should also be able to see in the other direction backwards. Right. Okay. So now, okay. So now here comes the big theorem that is really like how we treat these CSS codes, is that every vector in kernel of delta 1 modulo the image of delta 2 is the same logical Z operator and every vector in kernel of delta 2 perp modulo the image of delta 1 perp is the same logical X operator. And furthermore, these are a basis for all the logical operators. Okay, so let me parse what this theorem means piece by piece, and then let's work through it. And each part, once you kind of understand the definition of what was being said, it follows rather immediately. Okay, so far we saw, let's look at, we had this claim that any vector in the kernel of delta 1, you know, the Z operator corresponding to that vector commutes with all the X stabilizers and Z stabilizers, right? Okay, now I want to show that if I take that kernel and I modulo the image of delta 2, I get the same logical operator, right? So how do I show that? So let's go to the next page. So let's do so proof part 1 is if I have V being in the kernel of delta 1, right? And I have W the kernel of delta 2 perp. Okay. Then for all V prime in the image of delta 2, I'm going to have VW is equal to V plus V prime W. So what this means is if I take a operator in the kernel of delta 1 and I consider any other operator V plus V prime, which is, so that's just moving that operator by something in image of delta 2, its inner product with any X check should be the same. And this, the way you prove this is you just need to show that V prime W, well, this exactly like the previous proof we did a second ago, since V prime is in the image of delta 2, it's equal to delta 2 V tilde prime W, right? So that's the same thing as V tilde prime delta 2 perp W, which is equal to V tilde prime 0, which is equal to 0. And so that shows the previous statement. So what this means, if I have an operator in kernel of delta 1, it's equivalent to any other operator I could have done if I just moved it by image of delta 2, right? Is that okay? All right, I got a thumbs up from Anurag, so I'll take that as a yes. Right, and the second part here in this statement follows the same way, that it's just looking at the reverse picture. So I won't do that part. Okay, so now we want to show that this is all the logical operators. Okay, so proof of part 2 of this statement, that these are a basis for the logical operators, we can do this by a dimensionality argument. Okay, so the Z stabilizer group, all the stabilizers that can be generated by just Z, right? What's the dimensionality? They have a dimensionality of image of delta 2, right? It's precisely the image of delta 2. So going back to a point William said a bit ago, right? Even if there were redundancies in my check map, I'm handling them right now, because even if there are redundancies in the maps delta 2, right? All the vectors aren't linearly independent. At this point, the space that they span, all the stabilizers they span, its dimensionality is fixed here. So that's how we kind of handle that. So even if there are, even if the matrices delta 1 and delta 2 aren't independent, we're still okay, right? Analogously, the X stabilizers, well, their dimensionality is the dimensionality of image of delta 1 perp, right? Which is the same thing as the dimensionality of the kernel of delta 1 perpendicular, right? Which is going to be the size of A1 minus the dimensionality of the kernel of delta 1. And recall, this is the number of qubits. Okay, so the number of independent X stabilizers and Z stabilizers we've constructed so far is precisely the sum of this term and this term, right? So in order to show that we have found all the logical operators, by dimensionality argument, we just need to find the rest of them, right? So the number of logical operators we constructed here is pretty simple. It's just the dimensionality of the kernel . Okay, sorry, my pen froze for a second. Is the dimensionality of the kernel of delta 1 minus the dimensionality of the image of delta 2, right? And then now we can just add up all of these terms, and we add up everything, and we see everything nicely cancels, and we're going to get A1, right? So we're good. We have found all the logical operators. You can show the basis for all the number of logical X operators and the number of Z operators we found were the same. You just have to do the linear algebraic equalities to show that those two sets are the same size. And we showed that all of those logical operators that we did find were all independent, right, by this part 1. Okay, so let me just do a quick recap, right? Is we have a CSS code defined by two operators, delta 1, delta 2, right? And we found that the X stabilizers were the image of delta 1 perp. Z stabilizers were the image of delta 2. And we found that the X logicals were given by the kernel of delta 1, before I mess myself up, sorry, kernel of delta 2 perp divided by image of delta 1 perp. And the Z logicals were the kernel of delta 1 modulo the image of delta 2. So at least we were able to say what these things are. Okay. And this has so far been totally algebraic, and I think if I hadn't seen this before, I would be totally lost. So let's go back to our favorite example to kind of see this.
What do you mean by logical X operator and logical Z operator again?
Right. So a logical operator is an operator which commutes with all the stabilizer terms, but is not generated by the stabilizer. So the way I should think about it is if I apply this operator to a vector in the code space, right, it's certainly going to move to another vector. It's going to move to a different vector in the code space. But that this transformation is undetected by our error correction terms. So if I was to encode information in this space, I'd want to be able to at least manipulate the information, right? And manipulating the information is, we can think of as applying X checks and Z checks. Sorry, applying X gates and Z gates on different qubits. And so what we're precisely trying to do now is to find how I can think of these X gates and Z gates. So my error correction code is, we really should think about this as the stabilizers define a subspace, a much smaller subspace within the space of like n qubits, right? And now, if I look at this subspace and it's of dimension k, it's k qubits big, I'd want to be able to think about what does it look like to take one basis vector of this subspace and move it to another basis vector of the subspace, right? I want to be able to tell you exactly what that transformation looks like. And what I've done here is I've provided a basis for that subspace and what these logical operations look like.
So like X logical just means that the set of logical operators that are generated by X matrices?
Yeah. Right. Yeah.
I guess it's kind of a coincidence. Like in general, it means the set of operators that act as the Pauli X on the logical qubits. But for CSS codes, that happens to be the same as the set of logical operators that are tensor products of X's.
Yeah.
Right? It's not in general the case.
So which way is it defined though?
I think
in general, when people talk about the logical X for stabilizer code, they mean they're identifying something that acts as the Pauli X on the code subspace. So they've identified some vector as like the logical 0 vector, some vectors logical 1 vector, and then they want something that maps logical 0 to logical 1.
Okay.
So that's the general definition, if I understand correctly.
If your stabilizer had only X or only Z, couldn't you extract from any such logical operator only X part and only Z part? So, I mean, just to think about the coincidence that Anand mentioned, that CSS codes seem to have only X and only Z logical operators. I mean,
I think you can probably prove that from the fact that the stabilizers are only X or only Z.
Well,
right.
Yeah, we actually just proved it. So this is this is a way of representing X logicals and Z logicals. This is a basis. Recall, right? Like what we have here is a way of defining this subspace, this code subspace, and we're defining it using these operators, these X logicals and Z logical operators. They define a subspace. Now, certainly, I can define the subspace in a different way, right? A quintessential example of this is sort of this notion that, if I want to talk about information, I can, and I have some space, I can look at it in any rotated manner. I can just think about any rotation. I still have all this space, right? I have some information in space. I rotate it by unitary. I still have all that information. It's still there. It's just in the rotated subspace now.
Right.
Yeah. Okay, so let's do an example of the Torah code, and then this should be a nice, maybe a little clearer. So we're going to think of delta as the boundary map on the Torah code. So this is actually why we're using this delta notation, is because if you are interested in looking at this from a topological standpoint, this is actually, we can think of this as a boundary map. So a boundary map basically says I take a face. So if I have this face here, let's call it alpha. What I have is the boundary map is that it takes the indicator vector on alpha to the vector indicated by its to EA plus EB plus EC plus ED, right? It takes the indicator vector for that face to the set of vertices. And then, you know, if I had another face attached to it, it doesn't even have to be a rectangle, it could be any shape, right? This could be E and F. This guy could go beta. Then E beta under the boundary map would map to EC plus EE plus EF, right? And then by linearity, E alpha plus E beta would get mapped to, let's just short form this indicator on A, B, F, E, D, right? Is everyone okay with that? Right, because I look at the indicator vector and it now what I think is I just see that it ignores the C thing, it gets double counting. And I can also think of a boundary map for an edge as taking the edge G to the vertices 1, 2. So EG under delta gets mapped to E1 plus E2. So I'll let everyone kind of play around with this. But if I take these delta boundary maps as those coming from a tessellation of the toric code of a torus, I actually end up getting the toric code, right? Because in our toric code, the way Anna described it last time, right? Remember, I had one thing which was a Z check on every face like this, right? This was one type of check I had. And that's certainly what I'm going to get from this formalism, right? And for every vertex intersection, I also had an X check that came from this vertex. And this is really resulting in the same thing as the toric code that we previously looked at. So maybe I'll just say one thing about how one perceives this in algebraic topology language is this kernel of delta 1 is called a one boundary. And the image of delta 2 is called a one cycle. And the kernel of
Wait, is that flipped around? Because you'd think the kernel of a boundary map should be a cycle, right? Because things that have zero boundary are cycles. Or am I confused?
You know, I have my copy patcher right in front of me. I can take 3 seconds and make sure that I got it right. Yeah, no, it's boundary. I have it right. The names are, yeah.
That's very counterintuitive.
Oh, nope, no, sorry, I have it wrong. You're right. Okay, good. Thank you for catching it. Cycle, boundary, and the kernel of delta 2 perp is going to be called a 1 cocycle, and the image of delta 1 perp is called a 1 coboundary. And the way you can visualize this is if I take my torus, right, and I think of kernel of delta 1, it looks something like this. It goes around the outside like this. And so this is a cycle. And this guy here is both a boundary and a cycle. So recall, because we showed that kernel of delta 1 contains image of delta 2, that all boundaries are cycles, but not all cycles are boundaries. All right. So this actually leads us to a very specific point, which is our CSS code contains qubits, contains logical qubits, if and only if kernel of delta 1 does not equal the image of delta 2. And this also is sometimes referred to as the homology group, H1, does not equal 0. That's another way of saying this. So one of the reasons why we needed our simplest example was a toric code instead of just maybe the same kind of construction of boundary maps on a sphere, is if you looked at a sphere, you actually find that the kernel of delta 1 equals the image of delta 2. On a sphere, every cycle is a boundary. You can kind of work that out if you'd like, which shows that if I was to construct a code on the sphere, it won't encode any logical information. It just defines a state. So really what happens actually is if you add all those stabilizer terms up, if you did the same construction with the sphere, you're going to get a stabilizer which defines a singular quantum vector. A very interesting quantum vector, but there's no space here.
Can I ask what's interesting about the quantum vector?
Oh, I mean, well, so there's this nice paper by Dorit and her student Jonathan, which actually showed that this vector has high circuit complexity. You can show that it cannot be constructed by any circuit of depth shorter than log n, even though this code doesn't have, which is something you can show for codes with distance, and there's a whole set of arguments this way, but it's highly entangled is what you can prove.
Thanks.
Yeah. Okay, I'm on page 7 now. Okay, so far we've talked only about rate, so to speak, right? We've shown that the rate is just the number of logical operators. So we need to, and we've shown how many that is. Just this, it's this ratio kernel of delta 1 divided by image of delta 2. Well, let's talk about distance. Okay, so the distance of the code, right, is yeah. Okay, sorry. I accidentally pressed the back button and okay. Distance is the size of the smallest logical operator not equivalent to identity. So any logical operator that is in image of delta 2, for example, any z operator in image of delta 2 is equivalent to identity, right? It's just, it can be generated by the stabilizer. So if you apply that operator, it doesn't change the state, right? So yeah. So we can think of this as distance z is the min size of kernel of delta 1 modulo image of delta 2 And analogously, I could think of the distance in the x direction as the min size of kernel of delta 2 perp modulo image of delta 1 perp. And I can think of the total distance as just the min of distance z.
Sorry, isn't a logical operator not equal to the identity by definition?
So yeah, so it depends on how you want to define it. I find it easier to think of just there's a bunch of logical operators which are equal to identity, and just okay. So maybe I wrote that. You could think of everything that commutes with the stabilizer group as a logical operator. Some of them might just be equal to identity, right?
Sure.
If you do that, then it's nicer because now you can work with the whole group theory, because now you have an identity in your group, right? So maybe and the distance is going to be the minimum of this distance z and this distance x. Now, why this is exactly the case is not too hard to see. If you had a logical operator, which is small, you can always break it up into its x part and z part, and you can look at them separately. It's kind of the whole fun stuff we've been doing here. Is everything kind of is of an x type or z type, so we can break stuff up very nicely. Okay. So this
just one quick question.
sorry.
Anand and I were talking earlier, and he said he found something in like the press school notes where press school is claiming this is like maybe a lower bound for the distance. Wasn't that right, Anand? Or
Yeah, let me pull up what he actually says. I think he illustrates it with the short code.
yeah, he said something like, oh, the 9-qubit code, if you actually use these formulas, you would get a distance of 1, but for some reason the distance is actually 3.
Okay, so I don't really understand that, because
May I guess what that means?
Yeah, go ahead.
I guess it just means that you can correct some other errors with higher weights. This tells you that the minimum weight that it guaranteed that you can correct every error that is smaller than this weight. But there might be some errors with higher weight that you can correct.
So one thing I noticed that this excerpt uses the word degenerate, that like this this condition like guarantees that if you have errors less than the weight you get out of this formula, then the code is non-degenerate. But I guess if the errors are higher than this weight, you could have multiple errors that map to the same syndrome. So that gives you like a logical operator, right? But it's still correctable.
yeah, so this is certainly the size. So this is certainly the size of the smallest z logical operator, and this is the size of the smallest x logical operator. I'm a little confused because maybe we can talk offline.
Yeah, I think so.
Anyone interested? Because there are these conditions for error correction known as the Knil-Laflamme conditions, which actually are a little strong. We haven't talked about anything of this nature, but they actually show when is not only is it correctable, but it's also recoverable. You can actually, even if an error occurs, you can return back to the state. And in which case you could show that if I took the logical operator which satisfied this size, it would break the Knil-Laflamme condition. It would take you from one vector to another one, and they would no longer be orthogonal. So I'm a little confused, but maybe we can table that offline. So
yeah, we can try to read the press school notes later.
Yeah. Okay. Great. So now we at least have kind of realized how to see all the properties of a CSS code from these maps delta 1, delta 2, and one could just algebraically bash it out for any delta 1, delta 2 maps that you decide. But really the name of the game is, how do you discover these boundary maps delta 1, delta 2 that, actually have some value. Okay, so one idea is to sort of build these from geometry. So one thing we noticed is if I took this from like a tessellation of a space, I said faces, edges, vertices, like I did for the toric code, I certainly got something of interest. And I could even start drawing kind of crazier objects. I could draw the 2-hole torus, right? And if I did this, I would get, what I can show is that I actually get more logical qubits in this space. So the torus had 2 logical qubits. This one actually has more. How many does it have? Well, here's one logical loop. Here's another logical loop. Here's another logical loop. And here's another logical qubit. There are 4 qubits encoded in this space. You can show that this thing encodes 4 qubits. So you can go further. You can say, okay, if I decide objects from higher topology, what do I get? Okay, so turns out if you are just restrict yourself to objects that are 3-dimensional, I'm sort of restricted by the genus. The number of logical qubits is defined purely by the genus. So one could go a little further and say, okay, what if instead I didn't restrict myself to cell complexes A1, A2, A2, A1, A0, but I said, let me just think of a generic cell complex, which is I just keep going, right? AK minus 2, And I look at a cell complex higher up where I just have this property that delta K minus 1, delta K, still is equal to 0. So this would be like looking at higher homology groups of a object. I know instead of looking at just faces, edges, and vertices, I might now think, let me look at volumes, faces, edges, and see if I can construct anything better, right? And you can look at higher and higher homologies. And in fact, there was a recent paper on what if I did this with the Boolean hypercube. And I just thought of, the Boolean hypercube is a well-defined, I start with my vertices, I define my edges, I define my faces, my volumes, my 40 volumes, et cetera. I just keep going up and up and up. And instead of looking at the code constructed by the boundary maps delta 1, delta 2, I look at delta K minus 1. Okay? And that's something that has been analyzed also. And in this analysis, really the kind of what is interesting is we always need to think of kernel of delta K modulo the image of delta K plus 1. And this is known as the kth homology group. And maybe now I should actually address, I think, something William brought up last lecture is we were talking about homology versus homotopy. And this is where you have to think about homology, not homotopy, which is, and the homology is the abelianized version of the homotopy. Okay. So far, I sort of just wanted to say that what we've done so far is completely generic to cell complexes and really is a property of cell complexes. Because in a second, I'm going to do something a little fancy, which is I'm going to take the product of cell complexes.
So a question before that.
Yeah.
So I think you showed that CSS codes are equivalent to just taking 3 such A2, A1, A0.
Yeah.
These objects, do they give you generalizations of CSS codes? Like if you take AK, A minus 1, and so on?
No, like the CSS code is really just defined. The CSS code is a property of just the 2 adjacent boundary maps with this condition.
Right.
Putting it in this framework of the chain complex just is nice because it gives us a tool to figure out, to find such instances.
Okay.
It may not be necessary to actually construct them. As soon as I have a delta 1, delta 2, such that they multiply to 0, I certainly will have myself a CSS code.
Right.
And there exists a chain complex which contains it, but yeah.
Oh, okay, I see.
So sorry. So the only reason so to get a CSS code out of this, we really only need to look at 2 adjacent boundary maps. It's just we sometimes look at what happens if you added more boundary maps, because this can help you study these objects or something.
Yeah, so the CSS codes we first thought about as, oh wow, we see this boundary map condition at low levels. Like Tor code is, if I do this with boundary maps for k = 1, right? But we kind of hit a wall thinking about these boundary maps in low dimensional geometry. So people thought, let's try to find boundary maps that are good from high dimensional geometry. Right? It's the classic thing that you hit a wall trying to figure something out, and so you generalize to try to find inspiration. And this boundary map condition is something heavily studied in algebraic topology, right? So why not try to find my CSS codes from algebraic topology? Does that make sense? Okay, so I'm going to make an assumption here that I hope is justified, which is that if people understood the chain complex so far with the boundary maps at delta 2, delta 1, they would be okay with a sequence of these boundary maps that are not just 1 or 2 delta maps together, but a lot of them. Because we're going to do something interesting here on slide 8, which is we're going to take the product of 2 chain complexes. And we're going to show that this guy is still going to be a chain complex, and it's going to inherit some properties from the original chain complexes, which is going to be super nice. So I'm going to think of my chain complexes. I'm going to have a chain complex, which is, I'll call it A. So it goes AK minus 1, dot, dot, dot. And I'm going to think of a second chain complex, which I think of as the B's. So it goes BJ minus 1, dot, dot, dot. And I'm going to create a new complex, which I'm going to call E, and it's going to be the product of A and B. Okay, so there's a nice picture that one should generate when thinking about this product of cell chain complexes, and it's the following one. So I draw AK minus 1, and I'm going to think of this as a set. So this is the set AK plus 1 here. Okay, there's a boundary map here, and it takes me to AK. I'll think of that as a set here. And it's another one, right, which takes me to AK minus 1, etc., etc. And I can think of this as my BJ. Let's say plus 1, BJ. And I think of my boundary map going this way. So I have boundary maps as far as I want going in this direction, and as far as I want going in this direction, right? Okay. Now, here's what's going to happen is for every pair here, I'm going to have the set, which is the product of these two guys. Okay, so I'm going to have certainly sets like this. So what that means is that this is literally the product of the two sets. So every point can be identified as a point coming from AK minus 1, AK plus 1, and every point coming from BJ plus 1. Okay. And here's what I'm going to define. I'm going to say the nth level of my product, okay, is going to be the disjoint union over K plus J is equaling to L of AK tensor BJ. So what that means is that I sort of have something that looks like this. So this guy here is one element of EL plus 2. Okay. And these two together here, this one and this one, are part of the same level. So the level, right, recall a level of a chain complex is just a set. The level is defined as the union of all of these guys. So, you know, like this is, this product goes on, it's everything in this diagonal row. And similarly, these guys here, this one, you know, and the one that would be down here are together in one level. So does that make sense? The level is the union when I look at this diagonal picture. Is everyone okay with that? I've just defined the levels. I haven't defined the boundary map yet.
But just check, like the elements in EL, like they're not even all of the same type, right? For different like Ks and Js, you get just totally different vector spaces potentially, right?
Oh yeah. I'm just EL is just a set, right? And the way I can identify the set through this structure. Yeah, perfect. Yeah, well said. Okay, so now I want to define the boundary map. So, okay, so I'm going to define the boundary map DL is defined per space AK cross BJ. So here I'm just assuming L is equal to K plus J. Okay, so, and the way it works is DL of a vector UK tensor VJ is going to be DK UK, so the boundary map applied to UK, but I preserve VJ, plus UK with the boundary map applied, DJ, VJ. So what you should see is this guy here. This is going to be an element of AK minus 1 tensor BJ. And this element here is going to be an element of AK tensor BJ minus 1. So there's nicely a picture associated. So think about this point. Okay. Let's assume that the same point that came up in AK plus 1 here. All right, so that point, so this is just the shadow there. Let's assume for a second that it only has one boundary arrow and it maps to some point right here. So, okay. Then, and this guy also, for simplicity, or I guess I could do this. No, hopefully not that good. Its boundary map looks like this. It maps to 2 points there. So then the result, when I take this map, is this guy gets mapped to 2 points. It gets mapped to there. And there. So maybe this is a little confusing. I've drawn the boundary map as an arrow. You can just think of that arrow as if that indicator vector, if I take the delta map, which all, you know, what the support is. Does that make sense?
Oh, I'm slightly confused. I thought the EL was like a disjoint union of AK tensor BJ, but now it looks like when I apply the boundary map, I get something that's a direct sum of different elements in like EL minus 1.
Yeah, well, I should get elements. I should get a vector in EL minus 1, right? So I take the boundary map takes a vector with basis EL to a vector space F2 to the EL minus 1, right?
I see, but so, EL is like the direct sum of those things? I thought it was, disjoint union.
Well, E is the set, which is the disjoint union, but then the boundary map acts on the vector space.
Right, so exactly.
Over the set.
Right.
I think I understand.
It's like E is the set of faces in the toric code, and then the boundary map will act on vectors whose coordinates
it's like coordinate space. Your space now is like F2 to the EL. Is that right? Okay.
Right. So we can think of a basis in the toric code example. A basis for A2 is every face, and a basis for A0 is every vertex, and a basis for A1 is every edge. Right. That's what I can think of it as meant for the vector spaces. So yeah, it's a little complex. You really these are sets that, these are vector spaces, and I apologize for confusing people with switching between the dimension of the vector space and the vector space willy-nilly. So
this definition, it ensures that delta square is 0 again.
Yeah.
Okay.
Yeah. So there's two ways to see that. Anurag was asking, how do I check that this preserves the boundary map? And the one way to do that is I can actually calculate what delta L minus 1 delta L of UK tensor Vj would be, right? And so that would be just like applying delta L minus 1 to this guy here, right? And so if I did that, I would get out delta K minus 1 delta K UK tensor Vj plus delta K UK tensor delta J Vj plus UK tensor delta J minus 1 delta J Vj plus delta K UK tensor delta J Vj. And now we can see that this thing is equal to 0. Why? Because let's look at this term, right? This term right here, I have a delta K minus 1 delta K, right? But that's just 0, right? So this term gets nixed, right? And the other guy over here also gets nixed because it has a delta J minus 1 delta J there, which is 0. And these two terms are the same, so their sum is 0.
Thanks.
Maybe a little bit more geometrically, the way to see this is if I was to look at what was going on over here, right? Here's my point that I started off with, my UK Vj, and it got mapped to these 3 points here, right? And now I apply the next map forward. This guy is going to get mapped. If I apply the delta L minus 1 map, this guy gets mapped here, and this guy gets mapped here, right? And there will be some mapping going forward into the next guy also based on where this guy maps with. And then this guy gets mapped right here. This guy gets mapped right here, right? So anything in this object here got mapped in 2 different directions, so it came to 0. And now we have to worry about maps that go this way, right? But what do I know is if I take the map that goes from here this way, right? It's 0, right? Because I have the product of 2 consecutive maps in this picture is equal to 0, right? So I know there's no edges going forward this way. Does that make sense?
Yep, does.
Yeah.
Thanks.
So yeah, so there's 2. So you can see this geometrically, or you can see this algebraically. Okay. So why did I do this? Well, I did this because, like every other time I've done anything today, is this generalizes the toric code. So I can think of a toric code in the following structure. I think of the cell complex for toric code as just A0, A1. And I think of B as a cell complex B0, B1. Okay. I think of these guys as repetition codes. So the way I think of these guys is they look like the following. They are just, a repetition code is just the boundary map of this graph, right? Of a cycle. So I think of this as my A0, A1, and also my B0, B1. Now let's see what actually happens. And so here's what's going to happen. When I take the product, my E2 is going to be my A1 tensor B1. And I want to think of this as my Z checks. My E1 is going to be my A0 tensor B0 union my, A0 tensor B1, A1 tensor B0. And my E0 is going to be my A0 tensor B0. And what am I seeing this as? I'm seeing this as my Z's, my qubits, and my X's. And why is this the case? Well, let's just notice the following object. So let's look at a subset of the repetition code, which looks like this. So it goes this way, and I have another guy that goes this way. So, and now I want to compute exactly what that what the cell complex product is. So, right, so cell complex product, what occurs in E2? Well, E2 is the right, is the product of A1 and B1. So whenever I have an element of A1 and I have an element of B1, I have an object. So let's draw that. So I should get out something here. I should get out something here, right? That's the product of A1 and B1. So there's 4 objects so far in this drawing, right? And now what happens in my A0 tensor B1? Well, my A0 tensor B1 is when I take a point from one side and I take an edge from another side. So that's precisely this guy, this guy, this guy, this guy, this guy, this guy. And what happens in my, so that's this. And what happens here, well, those are these, this one, this one, this one, this one, this one, this one, right? And then the last thing that we need is this. When I take the product of 2 vertices, I get this. So what I see is that if I take this product of this A0, A1 and B0, B1 repetition codes, I indeed get the toric code as a cell complex. So toric code cell complex is a nice structure as a product structure. That's the first thing we realize here with this. Is everyone okay with this, what I did here? Right, it's kind of cool. And this isn't the only thing that one can do. In fact, there's some other examples. Here's other examples. Is if I take A0, A1, and I take B0, B1 as expanders, okay, then the product that I get is going to be an n to the 1/2 code. And this is by Tillich and Seymour. And what they really did is just realize this way before people realized this in 2009, way before people realized what was actually happening here is this cell complex picture. And let's do one other, which is if I take A0, A1 as an expander of size n to the 1/4, okay, and I take B0, B1, B2 as an n to the 1/2 n to the 3/4 code, okay, then the product, when looked at the second level, so remember we can derive a CSS code by looking at any level of this. This is going to be equal to an n to the 3/5 n to the 3/5 code. So this should be familiar because this is kind of what we're going for. Remember the whole reason we're doing this is to try to understand the new result, which is an n to the 3/5 n to the 3/5 code. So one of the steps that they use in order to do that is actually this cell product. And so what they actually do is they say, I actually only need to create an n to the 1/2. Sorry, let me be more precise.
Is this a construction that allows you to take a code that has like a really good z distance
Yeah, sorry. So
and another one with a good X distance and combine them together where they're like balanced.
right. So this, sorry, that's what I meant to say is that this is actually the distance here. So they take a code which has a difference in the z distance and the x distance, and this technique, this product of codes, if you take the product of this A0, A1 being an expander of this size and B0 and this B code being a code of this structure, you actually get this product. Okay. So let me say one more thing, which is what are the properties of this product? And then maybe I'll finish for the day because I think it's been a lot. Okay, so first I just recall for a cell complex, if I have a cell complex, A is equal to, so like this, then if I try to create a quantum error correcting code from the pth level of this guy, then n, the number of logical qubits is going to be the size of the pth level. The number of physical qubits. Number of logical qubits is the dimension of the pth homology group, which is the dimension of kernel this divided by image of this. And the z distance is also sometimes known as the size of the smallest p systole. I'll just write that here, but I won't. The definition is exactly what I'm writing right now, is the minimum element v, which is in the kernel of delta p modulo the image of delta p plus 1. And dx is just sometimes known as the cosystole, being the minimum of the size of v, such that v is in the kernel of delta p plus 1 star modulo the set minus the image of delta p star. Okay, so that's what the properties are for a cell complex. And nicely, what we actually get is when I take E to be a tensor B, number of qubits is going to be the size of EP, which will be the sum over the size of AJ BL product, where J plus L is equal to P. K will be the dimension of the direct sum over J plus L is equal to P of the homology groups that come from these codes. Sorry, not P. Which is equal to just the sum over dimension of Hj of A, dimension HL of B. Right? So I get the distance, the x distance is this, can be computed exactly by the distance from the original code. So what nicely happens is when I take these cell complexes and I take their product and I try to understand this, is I actually get a very nice structure for whom the code properties are very easy to calculate given the code properties of the original guy. Is that okay to everyone? All right, so let me just say this is conjectured by me. I tried to prove it last night to make sure it was correct, but I couldn't figure out how to do this. So this is I certainly know it's true for some very simple cases, but I don't know how to prove it in general.
Is there like a two-sentence intuition for why that's true? Like,
So I think the analysis of the distance is done in some paper from August by Kaufman and Tesler. So I think that was like quantum LTC p codes with root n times log to the kn distance.
Yeah, so they exactly analyzed.
Right. But I think like they're
I think that was the first.
Oh, sorry, I was just going to say the
first
version
paper
for the
that-
distance is not this, I think.
Sorry, say that again.
Yeah, I think so. They get a lower bound on the distance, the x and the z distance, and I think it's that's like the minimum of like instead of a sum, it's a minimum, and they have some like constant factor in front of it.
Okay.
So,
yeah. Okay. So maybe I should say possibly false. But I do know the homology, that the number of logical qubits can be very well understood by this coming from the two codes. So now I guess maybe the right thing to do is pause, see how everyone's feeling. It's been almost 100 minutes of me just talking nonstop. And I'm sure everyone's rather confused. There's, I think, three different directions that are very reasonable for us to take for maybe the next 5 or so minutes. One is we can just all call it quits and go to sleep. Second thing we could do is I could prove some of these distance lower bounds in the case of the product of cell complexes when the cell complexes are really short. So they're just level 1 cell complexes, the two of them. This was first done by Tillich and Seymour. Or maybe I can say a little bit high level of what is done in the new paper, the bundle codes. What would people be interested in?
I just wanted to clarify, as someone who's looked at the Tillich and Seymour paper a while ago, so that's just the special case of this when you have level 2 chain complexes. Is that all they do?
Yeah, that's all it is. So it's on.
Okay.
Yeah, so exactly. They just hit, but it's level 2 chain complexes A0, A1, B0, B1, and they need the A0 and A1 and B0, B1 to be expanders. So, and they referred to this in that paper as
Hypergraph product codes.
Hypergraph product codes. Yeah, a classical error correcting code you can think of as a level 1 cell complex, and you can also think of a graph as a level 1 cell complex. And so, unless you see the bigger picture as like, oh, this could be very naturally generalized to higher level cell complexes, it's not entirely obvious, and so that's why they call this hypergraph product of codes. But really, what this is it's a special case of this hypergraph product of cell complexes. Yeah.
I just have a small question on like terms. Is a cell complex and a chain complex, are those interchangeable?
Okay, so I'm definitely not the right person to ask. I think I've probably been using them interchangeably. Chain complexes in algebraic topology, as far as I know, are a little bit more complex. They're often uncountable sized, whereas what we have are all countable sized. They're all finite in particular, right? Every vector space is finite sized, but yeah. So I don't know. I might have been using them incorrectly, more likely than not.
Thank you.
So I was going to say that a cell complex is a particular type of topological space, whereas a chain complex is like this algebraic object with a sequence of vector spaces and so on. I think a cell complex is sometimes also called a CW complex. I think those are interchangeable.
Uh-huh.
Cool. It might be, I don't know. I mean, if people really want to see the fiber bundle stuff, that'd be cool. But I think it might also just be a good stopping point for
Yeah.
today, since we've gone for a bit.
Yeah. The fiber bundle you should think of as kind of like the product, like this hypergraph product, but with a twist. So maybe you're familiar with ideas like semi-direct products of groups, products with a twist, products with an identification, inserting like a, maybe I'll say that, maybe I shouldn't say anymore and hold it off for next week. So.
Cool. I don't know, Anand, do you think this is a good stopping point?
Yeah, it seems like a lot of material to process for me. So.
Okay, well, good. Yeah, thanks for giving this very interesting talk, Chinmay. Probably, I guess we can conclude with this, and we'll figure out a good reading for next week. Yeah, people can stick around if they want to discuss, maybe ask Chinmay some more questions. But also feel free to, I guess, head out at this point.
Sure. I guess I'll stop the recording at this point.
Yeah, it'd be good to also send out this link. I think this